Hello and welcome. I'm Patrick Cunningham, and along with Judy Colby-George, we will be your moderators for this virtual MEGUG Brown Bag Lunch and Learn. Today's Lunch and Learn, we're very happy to have Dan Martin from NOAA presenting on the upcoming new datum changes. All attendees are currently in listen-only mode, but if you have any questions for Dan or for any of us, please use the questions panel and we will do our best to answer them. This is meant to be an interactive kind of conversation with our speakers, and we hope that you will pepper us with a lot of questions and engage us. This is meant to be something for you as members of the main GIS user group and the greater GIS community. And we're here to hopefully provide some new information and share some educational points along the way. Of course, I have to ask all of our MEGUG attendees, did you renew your membership this year? We'd like to remind you that the main GIS user group is a nonprofit organization that promotes awareness of and encourages the coordinated development and effective use of geographic information and related technologies. We try to focus our efforts in the area of policy liaison, networking, research, education, and public relations. And MEGUG facilitates discussions and exchange of information and ideas in these areas by hosting regular meetings, workshops, and roundtables that are open to both members and non-members. And as you know, we've had to pivot this year like many other organizations, and our pivot has been to our virtual lunch and learns, and so far they've been a great success. So we're very excited about that, and we're very excited to bring you another one in our monthly series. We'd like to thank our gold sponsors, Quantum Spatial, Blue Marble Geographics, and Esri. We'd like to thank all organizations that participate and support main GIS user group. Certainly appreciate all your support. The MEGUG board is made up of volunteers from around the state. You can see the list here on this slide. And I'd like to remind you that we are having our annual meeting coming up and we will be holding elections. So if you're interested in participating, we would love to hear from you. Speaking of which, other upcoming virtual brown bag lunch and learns, next month we're going to be doing a discussion on the issues with mapping and tracking COVID-19 data with Dr. Megan May from the University of New England with the Microbiology and Infectious Diseases Division in the College of Osteopathic Medicine. That should be a very interesting and timely discussion. The following month, November 10th, will be our annual meeting where we will hold those elections that I just mentioned. And we will also have, it'll be a little bit longer. This will be an hour and a half. We'll have some presentations from our gold sponsors, and we'll have a presentation from Maine Fisheries and Wildlife on eagle recovery. That should be an interesting talk as well. In that meeting, we will update you on what we've been working on the past year and what our plans are for 2021. And then in December, we have slated a talk on high resolution land coverage and forest mapping products for Maine. That too should be another great conversation. The date has not yet been set, but watch our website for more information on that. The registration information is available on our website for our October 13th and November 10th meeting, so I encourage you to register. And just as a side note, all of these lunch and learns, we have been recording them and posting them on our YouTube channel. So follow us on YouTube. If you've missed any of the prior talks, you can go there at your leisure and catch up and enjoy the talks that we've hosted thus far this year. I'm going to hand it over to Judy to introduce our speaker.
Hello, everybody. We're glad to have you here today. And I have the pleasure of introducing Dan Martin, who works for the National Geodetic Survey and has been the Northeast Regional Geodetic Advisor since 2015. As the regional advisor, he instructs local surveyors, state and municipal agencies, and the geospatial community at large on how to use and preserve the National Spatial Reference System, and provides a liaison between the National Geodetic Survey and the states of Maine, New Hampshire, Vermont, Massachusetts, Connecticut, Rhode Island, New York, and New Jersey, as well as other federal agencies. He worked in the Route Survey and Geodetic Survey sections of the Vermont Agency of Transportation from 1988 to 2003, and he held the position of Geodetic Program Supervisor for the agency from 1999 to 2003. In 2003, he began his career with the National Geodetic Survey as the Vermont State Geodetic Advisor. Dan is a past president and fellow member of the American Association of Geodetic Survey. He is also a member of the Vermont Society of Land Surveyors and the New Hampshire Land Surveyors Association. So we'd like to just welcome Dan, and we look forward to his presentation.
Excellent. Thanks, Judy. Just before I give you control, Dan, I'm going to ask our poll question. I'm going to launch that. It's asking if you were aware of the upcoming datum changes before this webinar. You should see that in the chat, and you can respond to that question while it's up. Dan, I'm going to make you presenter now.
Great. Thanks, Patrick. There, should be seeing it now.
Yeah, so I don't know if you got that, Dan. The 67% of respondents were aware of the upcoming datum change, but 33% said they were not.
All right, that's interesting. I guess I would have expected it to be a little higher than that. I wouldn't expect 100%, but 2/3 is a little bit lower than what I expected. So,
Yeah.
all right, well, great, thank you. That gives me a little perspective going into this discussion. I will admit that I've taken a little bit for granted as far as folks' knowledge of the impending changes to our datum. And knowing that that's not 100% the case, I apologize for that. But I am sure that we will get the gist of it, and certainly can take care of other things with follow-up questions. There we go. So let's get the big question out of the way first. So what is the National Spatial Reference System? And for those who aren't aware, we consider the National Spatial Reference System to essentially be these quantities: latitude and longitude, or northing and easting, height, scale, gravity, orientation, the things that, generally speaking, positioning professionals need to create maps. Right? We need orientation. We need some physical knowledge of some physical quantities like gravity. We need to understand heights. So that's what my agency does. That's our official mission, is to define and maintain the NSRS for our nation's economic and social needs. But in today's world, we also have to recognize that we have to be able to monitor and maintain these systems based on the fact that they're changing. As much as we want to believe that we live in a stable environment, we know that that's not true. We have certainly lots of motions which are natural in nature, whether you're on the West Coast and you had an earthquake and things move. You're in southern Louisiana or coastal Texas, and there's subsidence, so heights are changing. And if you live in the Northeast, whether we know it or not, we have vertical motion. I'm sure we have horizontal as well, but we have vertical motion due to post-glacial rebound. So, tens of thousands of years ago, we were covered with a glacier, which depressed the crust. The glacier melted, the crust rose, and it's still rising today. Not a lot, maybe on the order of a millimeter per year, but over decades. You think of our geodetic leveling network and our height system that's been developed over the last 80 to 100 years. Certainly there's been a lot of change in the physical location of those monuments relative to each other. So the NSRS is as we consider it, are these quantities, and also how these change with time. So there's been a number of different datums and realizations and coordinate systems that we've used. Probably most of us are familiar with, at least those who have been in the profession for a while, with NAD 27. You probably still work with data in your GISs that originated in NAD 27. It's probably been transformed, but sometimes we work with that. NAD 83 obviously is the prevalent datum today, and that's represented typically in latitude, longitude, or state plane coordinates, maybe UTM coordinates. But is NAD 83 the full answer? Right? And the answer is no. We've had a number of different realizations of NAD 83. The original being in 1986. In the 1990s, we came along with these concepts of high accuracy reference networks, which were GPS based. And then a follow-on project for what was called the Federal Base Network, again GPS based. We developed the continuously operating reference system, the CORS. And our first true realization of a CORS-driven reference frame or datum realization was in 1996 with an epoch of 2002. And then we had a national readjustment of all of our GPS in the country. That was the NSRS 2007 adjustment. And most recently is the NAD 83 2011 adjustment at an epoch of 2010.0. So you can see in this last one, we've introduced that time period, right? That epoch. So that says here are the coordinates and here is the date, right? January 1st, 2000, January at midnight, December 31st, right? At midnight, 2010.00. So there's our introduction of a time epoch as to when those coordinates are relative to. But the thing to think about here is that not all of these NAD 83s are equal. Okay, if I put out a coordinate for anyone, and we'll see an example of this later, if I put a coordinate out for a mark in any one of these different realizations, it's in a physically different location on the ground based on the coordinates. Okay? So keep that in mind as we move forward when we start talking about metadata. Some will claim that their surveys are in WGS 84. We don't have time to argue about that today, but the reality is sure, you could be tied to WGS 84, but even still, which one is it? There have been a number of different actual datum realizations of WGS 84. So if you were to actually purporting data in WGS 84, it would really truly only be correct to if you indicated which realization, WGS 84 GPS week 730, for instance, or GPS week 1762. So and these have from the WGS 84 1987 up to WGS 84 G1762, there's about 2 meters of difference in the coordinate value for at the same point on the ground. So it can make a big difference. We're only looking about maybe half a meter, 3/4 of a meter or so on the NAD 83 side, but still, depending on the data that you have for your GIS, that might be important. And then there's other international frames too. We're not going to get into those, but just know that they exist and that coordinates often are purported in those datums. So just a quick word here about the International Terrestrial Reference Frame. That's the ITRF, the latest. It was released ITRF 2014. This is what we operate in. If you use GPS, whether you know it or not, you are working in ITRF. Now you've conveniently told your data collector to give you coordinates in NAD 83, maybe Maine State Plane East, but all the calculations, everything that's being done is being done in this international frame, and that's important to remember as we move forward. So today, when we look at NAD 83 and ITRF, those two reference frames are separated by about 2 meters, okay, 2.2 meters. So if you're getting a position autonomously, let's say from satellites, without it being post-processed or some sort of differential correction, it's in that international frame, and it's about 2.2 meters away from NAD 83. So that's not a big deal today, but as we'll see, it becomes a big deal very quickly. This is what the velocity of the international coordinates look like, and that's because the North American plate is rotating. So if we think about how we position ourselves today using GPS, and the fact that we're positioning ourselves on a moving plate. Okay, so the coordinates that I get for a point today in the international frame are not the same as the coordinates I get in 6 months from now at that same point, because the point has physically moved within that frame. And we'll see an example in a moment of how that works. But this becomes very important when we start talking about moving into the new frame and taking into account the fact that our calculations are being done in this dynamic frame. But yet we're still trying to show them as being stable coordinates on the North American plate. We'll see how that relates. And then, as we can see, of course, even within the continental United States, we have California, which does not look anything like the motions, this very systematic motions throughout the rest of the country. And that's because Western California is on the Pacific plate. So it's doing something totally different compared to the rest of North America, or at least the rest of the continental United States. And of course, then there's vertical motions too. Okay, so this is just an example of what that might look like. Vertically, our definition for heights is the North American Vertical Datum of 1988. This is how it's defined. Okay, at a particular point at the mouth of the St. Lawrence. More importantly, this is how our datum is realized by 500,000 or over 500,000 physical marks in the ground that have measured, published NAVD 88 heights on them. That is how we realize our datum today. Okay, and even if you want to take the next step and say, well, no, I get my height using GPS. Well, that's true, but the geoid model has been built. Okay, that the geoid model being the way that we convert a GPS ellipsoid height to a NAVD 88 orthometric height. That geoid model was created by including GPS observations on some of those published benchmarks. So without those published benchmarks, you wouldn't be able to get an NAVD 88 height with GPS, okay, because we wouldn't understand the relationship between the ellipsoid and the geoid. So the important thing to remember, though, is that this is how we realize our datum, by these physical marks in the ground, and that's problematic, right? So the problems we have with NAD 83 and NAVD 88 today, right, are the NAD 83. It's not as geocentric. It's that 2.2 meters, right? And we don't see that yet, but it's going to be very, very soon, right? Only a handful of years, but what you'll be able to go down to your local sporting goods store, buy a $99 GPS multi-constellation handheld GNSS unit, and you walk out in your backyard and you're going to observe 58 satellites all at the same time, GPS and GLONASS and Galileo and Baidu and whatever else might be around at that time. And you're going to be able to position yourself on the ground relative to those satellites, unaugmented, to about a decimeter. Okay, so now that 2 meters shows up like a sore thumb. Right, so this is one of the reasons why we have to do this, at least on the horizontal side. On the vertical side, if our datum is realized by these passive control points that we know, even in what we consider to be stable part of North America, right, like Maine and Vermont, we know that those marks, at least because of post-glacial rebound, those marks are moving. So do we know how much they're moving? Well, no, not really. Is that motion accounted for in our datum? No, it's not, right? The height for any one of those benchmarks is whatever's published on the data sheet. We don't have a velocity calculation that says that, oh, here's the height, and then add 1.3 millimeters per year, starting at 1960 or something like that, right? So there's no account for these vertical motions, and the fact that the marks aren't often revisited. They get destroyed on a regular basis due to highway construction, due to conversion of railroads to rail trails, replacement of telephone poles, right? A whole host of reasons these marks get destroyed, and it's just not cost effective to try to put them back in the ground the way in using the methods that we've used in the past. It just costs too much money, takes too much time. So here's our plan. first came out in 2008, our 10-year plan. It was then revisited in 2013. And our current target, as that plan states, is to replace NAD 83 and NAVD 88 by 2022. Okay, and we don't have time to go into all of the reasons today, but that 2022 has slipped to something more along the lines of 2024 to 2025. Again, not in great detail, but sort of here's the reasoning behind that. In 2018, we had 3 government shutdowns. The third one coincided with when our GravD program, which is how we're defining our new vertical system, was set to be deployed to the Pacific. And because of the cost and the availability to get projects done in the Pacific, that alone cost us a delay of 1 year. The growing complexity of what we're trying to do, the lack of replacement of very experienced personnel that we've lost due to retirements and trying to get new people in, and then of course everything associated with 2020 has obviously cost us some time. If you're interested in a full detailed explanation of why we've made this change from the 2022 to 2024-25, there's about an hour and a half long webinar on our webpage, and that's where it's located, or you can just search for Drew Smith's webinar, and it gives really all the details on everything. It's a great webinar, and if anyone's interested, I would encourage you to look at that. So we've made 3 scientific decisions relative to the change in the datum. So the first is the geometric. Okay, and geometric, you can think of that as a horizontal datum, but since it includes a height component, the ellipsoidal height, it's actually a geometric datum. We're defining 4 plate fixed terrestrial reference frames. We've determined and spelled out what plate fixed means. Okay, that's something that's important to do. You can't just say it's plate fixed. You have to say what that means and how you're defining that. We have all of the math between the international frame and what we're calling the new terrestrial reference frames. We're including a plate rotation model for each plate. Coordinates, a survey of epoch. All right, that's something that we don't really maintain so much today, but certainly within the international frame, it's important to know not what the coordinates are in NAD 83 2010. It's what are the coordinates in whatever my coordinate frame is at the time that I took the observation, right? And once I know that, then I can apply these other models in order to move that coordinate forward or backward in time through transformations. And then a more localized interframe velocity model. We'll see just briefly what that is. It allows us to compare coordinates at different times. Okay, so this is what the North American plate looks like. Okay, so we're looking at, about a couple centimeters maybe per year of motion within the international frame based on plate rotation. Right, again, California is sort of doing its own thing. Here's our 5 plates. I'm sorry, the 4 plates that we're building models for. So here's our current. We have NAD 83 2011. That's what we all use here, right, in CONUS. And then you've got NAD 83 Pacific and NAD 83 Marianas. So those are the 3 plates that we currently support. The 4 new plates, we're adding the Caribbean plate. So we have the North American terrestrial reference frame for CONUS. We have the Caribbean terrestrial reference frame for the Caribbean, the Pacific, and Marianas. Okay, so those are the 4 frames where the U.S. has territories or holdings that we need to support. So again, developing the 4 plate fixed frames, we're removing this non-geocentricity. So we're going to be moving the origin of our new terrestrial frames to what the origin of the international frame is. So we're shifting things at a minimum today of about 2.2 meters. We'll be aligning to the international frame of 2020 at the epoch of 2020.00. That's how we're defining the new terrestrial frames. And we'll remove most of that tectonic plate rotation through something called an Euler pole. Okay, but the important thing to remember is that as we make our measurements, those coordinates that are being determined, there's a shift, and then there's also an associated drift with those coordinates over time. Right, so the tectonic plate rotation part, that's easy to do. Okay, that's easy to model. The other stuff, the localized subsidence, the local horizontal motions due to plate tectonics and earthquakes, and those other types of things, those are harder and more complex. Okay, but these are the two types of motions we have to deal with. So this is sort of the idea of the concept of the International Terrestrial Reference Frame. You can see the, over the various historic periods that we've had, the plates have moved, and so they've redistributed themselves throughout the globe. But the grid that's on there doesn't move, right? That's our terrestrial or our international frame. That's stable, that doesn't move. Everything else is moving relative to it. As I said, we're defining something called an Euler pole. That Euler pole, if you see like the little gold star here, that essentially is like an axle of a wheel. Okay, and if we find the 0 point of rotation for the North American plate, that's where that star would be. So then we describe the motions of that of the plate with a latitude, longitude, and a rotational velocity or a rotational rate in radians per year. So that's how we're able to essentially to remove that motion in order to put things back onto a stable North American plate. All right, we'll see how that works here on this next couple of slides. So again, the international frame, the frame is constant and the plate is rotating. In the terrestrial reference frames, right, those things that are going to sort of replace NAD 83, those terrestrial reference frames, the frame is rotating relative to the international frame, but it's constant relative to the North American plate. Okay, and here's what we can illustrate that. So if we look, here's I'm going to go ahead and select the start button, so we can see here's the concept of ITRF. So there's our ITRF grid. Okay, let me back that up and do it again. And you can see the North American plate moving underneath the grid. So as you can see, the coordinates in Maine over time, right? The coordinates in Maine over time would change, right? Because the grid stays the same, but Maine is moving. Then if we look at the concept of our terrestrial reference frame, which is where the frame rotates with the plate, right? It looks like this, right? So the whole idea is to try to make our terrestrial reference frame be fixed and rotate with the plate, okay? So then if we look at the difference between the two, and you could use either one. You could either do work in the international frame or the terrestrial frame, right? You just use those Euler pole parameters and it would allow you to compare the two. So you can see for any given time, I can compare the two based on the difference between the two grids. Okay, so it's a fairly simple concept once you sort of wrap your head around what's going on, but that's what's going to have to be taken into account as we're collecting coordinates in the future, or moving coordinates through transformation. It's very important to know when that data was collected, what it's relative to, and what you need that information portrayed in, right? Which realization or which epoch it needs to be. So again, here's our course velocities in ITRF. Again, Pacific plate. If I apply the Euler pole, right, to that motion, then you can see that essentially almost all of the motion on the North American plate goes away. There's some little residual motions there. We can't see the vertical part. That's the one thing to keep in mind, is that the Euler pole parameters only takes care of horizontal displacement, not vertical. Okay, we can see now that the California still has all this movement. Why? Well, because California, for the most part, is sitting on the Pacific plate. So if I use the Euler pole parameters for the North American plate, that cleans things up on the North American plate, but not on the Pacific plate, right? So folks working in the western part of California would probably be doing a lot more work using PATREF, right, the Pacific terrestrial reference frame, rather than NatRef, because of the plate that they're actually on. So this is really, it's just sort of a little diagram that shows what you'd have to do. So if you're using GPS, you're getting your coordinates in ITRF. Again, you may not see them, but that's what's being computed, at least initially. And then if you apply this this Euler pole parameter, okay, the EPP, for the plate that you're working on, that transforms it from ITRF into any one of these terrestrial reference frames. The interesting thing is if I wanted to, right, in Maine, I could take the ITRF coordinates in Maine, and I could use the Euler pole parameters for the Caribbean plate, and I could compute CATREF coordinates in Maine, and they would be 100% mathematically correct, okay, because all of these are directly related through the same model. So again, whether you're doing it through GPS and it's taking care of it, or whether the transformation is taking place in your software, this is what's going to happen to move from ITRF into any one of the terrestrial reference frames. So again, the Euler pole part is simple. The interframe velocity model, that's what's a little bit more complex. It takes care of those residual motions, and also some of those, any of those local motions that are being caused by subsidence or by lateral motions along a coastline or something like that, due to plate tectonics or other physical effects. The one thing, let me go back here. The one thing to mention, right, is that the Euler pole parameter changes the frame. So that's your transformation, right, from the international frame to the local terrestrial frame on the North American plate. The interframe velocity model is how we change the epoch. And I have a slide here that shows that. So in order for me to say what's my coordinate, I determined a coordinate today, and here are its coordinates. I want to know what those coordinates are in 10 years. Well, the only thing I need to do is to apply this interframe velocity model. That's what takes care of my temporal transformation. Okay, so this is how that sort of works. So let's say we do a survey January 1st, 2023 at a reported epoch of 2020.0. And here's my point over on the right-hand side of my screen. Okay, and I have the NatRef coordinates, and I have the ITRF coordinates, and they're at the same epoch in this case, epoch 2020. Okay, 10 years later, I'm sorry, not 10 years, 7 years later, I do another survey on that same point. Well, in the international frame, we can see ITRF 2020 at epoch 2030, it's displaced now by about 15.5 centimeters horizontally and about 1 centimeter vertically, right? So we can see that the ITRF coordinates of that same point is now physically or mathematically, right, within the coordinate system, has changed by 15 plus centimeters horizontally and about 1 centimeter vertically. If I take those new coordinates in 2030 and I apply the Euler pole parameters for the North American plate, that gets me back to NatRef 2022, which is where I want to be, right? I want to be on the same terrestrial reference frame as my original survey at epoch 2030. Remember, the Euler pole parameter only transforms the frame. It doesn't transform the epoch. So here's ITRF 2030. I apply the Euler pole parameters. That gets me to NatRef 2022 at epoch 2030. Then we apply the interframe velocity model, and then that gets me back, that applies the local motions and gets me back to the same epoch. Okay? So that's sort of the concept of how those two transformation parameters work together in order to maintain coordinates and compare coordinates over time. Right, EPP does the frame, and the interframe velocity model handles the epoch. Part 2 is the geopotential or the vertical. Well, and we're not going to go into a lot of detail on this, but it includes a new geopotential model. Now, remember the one thing I said, right? What was one of the main problems of our vertical control network, or how we define our vertical datum? It was that it's based on physical points in the ground, which move, which we don't know how much they move, which we haven't tried to account for the movement, which get destroyed, and we don't have a program that adequately puts those marks back in the ground. So this is our attempt to eliminate that the need for the physical tied to a monument in the ground in order to realize our datum. So it'll be done strictly through GNSS and a geoid model. It's going to contain something we call GravD data. We're not going to talk about that today, but essentially GravD is the program to redefine the North American datum, or the American vertical datum rather, right? Gravity for the redefinition of the American vertical datum. That's what GravD stands for. Able to yield physical values on, above, below the surface. High rev, yeah. Okay, we don't need to go into that. Time dependencies. Does gravity change? Sure it does. All right. There's a lot of things that can change gravity, like very large displacements of mass, like a very, very large earthquake, or a very large landslide, like what happened out in the Pacific, or the wasn't small, Sumatra. Those huge events can actually change the gravity field of the Earth very slightly, but it does change it. What about the fact that we're melting billions of metric tons of ice that's all located at the poles, and now that mass is being redistributed through the oceans as liquid water? Does that have an impact on gravity? Sure, it will over time. So just like we have to take into account that our horizontal and vertical coordinates may be moving, we have to take into account that the gravity field may be changing, which is what affects our ability to measure heights. So we're implementing a geoid monitoring service that will take into account impacts of these things that affect our ability to, or that affects the gravitational field for the Earth. So on the name, so we have the old, right? We have our NAVD 88. We also have our island datums: Puerto Rico, Virgin Islands, American Samoa, Northern Marianas, Guam. Those are all vertical datums that we support as part of our system. Those are normal orthometric height datums tied to a local sea level, right? We can't get NAVD 88 out on those islands, right? Because remember, the only way to truly get NAVD 88 would be to go out and to touch an NAVD 88 benchmark and level from it to a new mark. And it's physically impossible for us to level from California to Hawaii, right? Just can't be done. And GPS, so since we have no NAD 83 bias geoid model in Hawaii, we can't get an NAVD 88 height out there. International Great Lakes datum, if you work up along the Great Lakes, gravity fields, geoids, all of that is being replaced by this new vertical datum or geopotential datum called the North American Pacific Geopotential Datum of 2022, right, or NAVD 2022, which will include geoid 2022. All right, so that's it for the vertical. So it'd be basically a GPS derived or GNSS derived ellipsoid height, and the inclusion of a gravimetric geoid model. That's what's going to define our height systems moving into the future. Right, so why does this stuff matter? Well, it's because the location of things matters. right? If you don't know where that fiber optic line is and you start telling the guy on the backhoe to start digging, you get pretty uneasy, right? You know, what if it says, oh yeah, here's the coordinates relative to NAD 83. All right, NAD 83 what? Right? If you're trying to locate something precisely, just saying NAD 83 doesn't cut it, right? We have to be much more specific. And as we move into the future, we have to be much more specific with everything else, right? Not just the datum, but the datum, the epoch, when it was collected, how it was collected. Those things may be very important to being able to represent that point accurately on the ground, or to go back and relocate that point accurately on the ground. So here's a quick example of that. Here is a point, and you can see on the bottom left where it says superseded control. Those are all the values for this point over, you know, the last 70 years or something. Okay, and so you can see that it was, you know, it was in the original NAD 83, and then NAD 8392, which is the Harn, and then NAD 8396, which was the FBN, and then 2007, and then finally up towards the top is the NAD 83 2011 position. And you can see that those positions over time vary by 6 decimeters, right? So if I had one of these coordinates, pick any one, right? If I had one of these coordinates and I just called it NAD 83 without being more specific about which realization of NAD 83 it was, you could see that I could have over 1/2 meter of slop in that position as to where it truly is, right? Depending on what the actual value was that I was using. So that's just an example. So, but if I take into account, right, if I take into account that I know that it was NAD 83 2011, and I know that it was NAD 83 2007, and so on and so forth, you can see that by using a proper transformation and taking that into account, now the very worst case scenario I have in this case is a couple of centimeters, and that's transforming the original NAD 83 86 position into today's system. So again, in order to keep, you know, a high resolution or high quality values of your data, or really just the integrity of your data, it's really important to capture more metadata than what many of us capture today. So again, datum, epoch, and the source, right? You know, if I say it's NAD 83 2011, only because I scaled it off of an NAD 83 2011, you know, a map that had NAD 83 2011 coordinates, well, that doesn't really do it justice, right? I need to say not just what the coordinate is, but how I got it. What did I scale it? Did I do GPS? Was it done by a total station survey? Was it through LiDAR? How was that determined? The best thing that, again, that we recommend is to try to maintain your original survey data, or your original originally captured data in some standard datum, some standard format with all of the appropriate metadata, and then you have the ability to move that through time and through frames with as much integrity as possible. So what are some of the things that we can do now? If you're not already working on the newest realizations, should probably start to do that if you can, and start collecting and documenting the metadata as thoroughly as you can, if you don't already do that. If you're a surveyor, obtaining precise ellipsoid heights on benchmarks, and then using the Opus Share option through NGS in order to help us build out a better vertical transformation model for the future, that's something that can be done. Maine could really use some more GPS on benchmarks. If there's anybody here online today that's a surveyor that's interested in doing some of that work, you can contact me later and I can talk to you about that. Again, on the vertical side, moving from NGVD 29 to NAVD 88, if it's possible, and do realize that you know, a transformation is just that. not just from a horizontal standpoint, but from a vertical. There can be, transformations in many cases are pretty good, but in some cases are not good. And so you may want to sort of do a little bit of a study of what the accuracy is of some of these transformations in the areas that you work, so that you have a good idea of what doing some of these transformations may be doing to your data. Move away from passive marks to using GNSS today. That's really going to be the model for the future. So it's something that you should probably try to start doing as much as you can today. That'll help you to start getting your workflow to work better for you in the future. And again, if you're doing contracts and that type of thing, make sure that you're requesting all of the metadata that's going to allow you to use that data with confidence in the future. Get that information, and don't just get the derivative products. If you have the ability to keep the raw data, which can later be processed into a different frame, then that's what we recommend doing. And the last little bit of this, of course, is a state plane, and a couple of things that are going to be a little bit different that Maine would be interested in, especially from the GIS side of things, is that NGS, in addition to Maine, for instance, today officially under NGS projections has two zones, Maine East and Maine West. We are still going to do a multi-zone layer for Maine. I'll show you what that looks like here in a moment. But we're also creating a single zone layer for every single state. So whether it's Vermont, Rhode Island, or Alaska, every state will have a state plane zone that incorporates the entire state, in addition to smaller multi-zone layer. Okay, and the reason is because a lot of the mapping professionals, the GIS professionals, trying to keep a statewide database in multiple zones is problematic. And in some cases, UTM can handle that, but even like a small state like Vermont, we have a UTM zone boundary that goes right through the state. So for many states, there's a zone boundary. So even within UTM, they're dealing with two different zones.
But even
so
for
this is what
even for the large states like Texas and others, are going to have one zone.
Yeah. Well, yes, they will have something that looks like this. Okay. So like Texas, I think has Texas or California. I think they have like 8 or 10 zones right now. So they and they will. We will have a multi-zone layer with 8 or 10 zones. But in addition, we'll also have a projection that covers the entire state.
Okay.
Okay. So you can you can minimize distortion by using these multi-zone layers. And so here's an example of what your distortion is. So currently in NAD83, through sort of the west side of the east zone, and I'm guessing that's where it's more mountainous. It gets up to up here into the minus 160 parts per million. That's the distortion level, or the difference between a horizontal distance measured on the ground and that same distance represented on the grid at the ellipsoid. So that's what that distortion is. So that's what NAD83 looks like today for Maine. Okay, this is what the proposed projection system for Maine is going to be under the state plane coordinate system for 2022. So we can say it's going to be 3 zones, similar to what the Maine 2000 is. I think the zone boundaries will be slightly different, and the central meridians will be slightly different, but it's essentially the same concept. So you can see now that for a couple different reasons, but one, we have the distortion for pretty much all of eastern Maine, and southern Maine really falls in the 20 parts per million range, which is really almost at the level of a low distortion projection. And then maybe up into the minus 100, maybe minus 120 parts per million out in western, west central Maine and in northern Maine. Okay. One of the things that we're doing here too, and we don't really have time to get into that, is that these projections are being designed to minimize distortion at the terrain level as opposed to at the ellipsoid. So NAD 83 zones were built to minimize distortion at the ellipsoid, which is why when you're working at 1,000 feet, you have more distortion. Okay. So now what we've done is we're designing these to more closely resemble distortion at terrain level. So the distortion level will be smaller. This is what the single zone for Maine is proposed. So it's actually, you'll see it's an oblique Mercator projection as opposed to a transverse Mercator projection. And that actually behaves very, very well. Even as a single zone, a good portion of the state is in the plus or minus 50 parts per million, which is just fantastic as a statewide zone for a state as large as Maine. But that is what we're proposing. So you could see then that instead of if you work for a state agency or you worked for a utility that had things that you were tracking or things in your database throughout the entire state of Maine, you wouldn't have to have them in individual projections. You could keep a database or transform any one of those files into a database that has everything in a single zone. Just from a mapping standpoint, that's pretty beneficial.
Are there such dramatic improvements with proposed zones for the other states? I mean, Maine has that challenge when you compare it to the ellipsoid versus terrain of being, at sea level for sort of that half of the state to get to the mountains, and then, we have the massive elevation changes. Is it as successful in the other states?
Sure. I think some states, depending on, I think if you go out west, you go out into the Rockies, right? And for Colorado, if you take a statewide zone in Colorado, it's going to be obviously high levels of distortion, and you can balance that to some extent, but it's not going to be ideal. So certainly Maine is not as dramatic, let's say, as projections. They're going to cover, multiple, many thousands of feet in elevation change. I know you have about 6,000 feet thereabouts, but you're talking about much more than that in some of these other states, and significantly different effects as you cross. So it's again, that's why I think that the statewide zone is just it's not ideal for all things, right? I mean, but it is a solution for being able to portray data statewide in one map, without having to deal with crossing projections.
Hopefully that will solve some headaches. I just like to quickly remind folks that if you have any questions, please do put them in the chat. We'd like to try to answer them. I think I'm seeing some questions come up here, so let me see if I can get that screen big enough so I can read it. Sorry. One question we have is, which definition of foot will be adopted going forward?
Oh, great question. Going forward, it will be what we call today the international foot. I don't know if it will be called international foot or if it will just be called foot, but definitionally it will be what we call today the international foot. So the U.S. survey foot is being deprecated, and I know people have different feelings about that, but it doesn't make sense to have two different systems of feet in the United States. And the reality is back in 1950s, we were supposed to make the change to the international foot anyway, and everybody did except for surveyors, and they were given sort of the option. Short answer long is it will be the international foot definition.
Yeah, that is a good question. And another question we had was, does Geoid 18 replace geoid 12A? Should we be using that?
Yes and no. And feel free, if I don't answer the question in enough detail, feel free to contact me later. But the geoid models that we use today are built by incorporating a GPS-derived ellipsoid height, an NAD83 GPS-derived ellipsoid height on a published NAVD 88 benchmark. And as you saw in one of those slides, we have a whole bunch of different realizations of NAD83. So if I use an NAD, if I collect NAD83 ellipsoid heights, NAD83 2007, let's say, all right, a few years ago, a 2007 ellipsoid height on a NAVD 88 benchmark, that gets me one, that helped me to build the geoid 12 model. Then when we came out with NAD83 2011, we used NAD83 2011 ellipsoid heights, and that helped us to create the geoid 18 model. So if you are using the most current realization of NAD83 in your latitude, longitude, and ellipsoid heights, then yes, geoid 18 would be the geoid model you would want to use. However, if you were working on a project or a real-time network or doing RTK on a benchmark or on a mark that only had an NAD83 2007 ellipsoid height, then you, by definition, you really should be using the geoid 12 model along with that ellipsoid height. So practically speaking, yes, NAD83 or geoid 18 replaces 12A, 12B, but it does matter which ellipsoid heights you're using in your project. That's really going to be the thing that dictates that decision.
And it's interesting. You know, this stuff is so complicated for the lay GIS person that I think sometimes we get a little bit intimidated and hesitant to ask questions. And that one's an interesting one because it's like yes and no. But
yeah.
So there's one question
and let me just interject for a second. And it's really, really important today that folks who are working in the geospatial industry understand that, because the vertical is becoming so much more prevalent in GIS products when you start talking about LiDAR and these other things where you know, the raw data from LiDAR is relative to an ellipsoid height. So when you try to create an orthometric terrain surface, it really, you know, it really does matter which type of which geoid model you might be applying to those heights in order to do that most correctly. So, you know, fundamentally, that knowledge needs to exist, you know, not just for surveyors, but for anybody who's working with that data today.
So an interesting question that we've had, and I had this question myself because, you know, working for Blue Marble, I had to study up on geomatics a lot on my own, and I had not heard of a Euler pole before, and so we had a question about how is the Euler, it's a pole, right? Or is it a Euler point configured, and how many are there?
So an Euler pole, it's an arbitrary, I guess it's pronounced Euler.
Okay.
But it's an arbitrary location, and basically it's by studying the motion of, in this case, plate motion. It's mathematically determining where the zero or where the axis is of that rotation. So that's really all that is that. So that Euler pole is just a mathematical determination of the center or the axis of rotation for that North American plate, and then the motions that we track are essentially the important part that we have is the latitude and longitude of that Euler pole that we've defined through mathematic inquiry, and the rotation rate of the plate. So a change in radians per year. So there's an infinite number of Euler poles depending on what it is you're trying to monitor, because you create it for any particular thing. I mean, but in theory, you could create a separate Euler pole for the state of Maine.
Mm-hmm.
It might be a slightly different location than it is for North America. I'm sure it would be. Physically, it would be, right?
Mm-hmm. Interesting. So a common question, I think, is, folks are wondering, when and what to do. One question is, should GIS users start using or move, it says start using the NGS single zone and retire UTM? It would give better grid to ground comparisons. I'm not sure if that's a question or a statement, but I don't have any thoughts on that.
Well, I mean, and of course, you won't start using the new state plane zones until the new datums are out. Okay, so you won't be, even if those projections are available, you wouldn't use them until NatRef comes out.
And and you're saying right now that's about 2024, is it?
Yeah, somewhere in the 2024-25 timeframe is what we're looking at right now. But if you were concerned with distortion, and again, distortion to me is just a mathematical formula, right?
Mm-hmm.
you take one distance, multiply it or divide it by something else, and you get the other distance. It's not that big of a deal to me. But if distortion is something you're concerned with, then I think you'll find that the single zone main projection will perform much better than the current UTM zone would be. And again, the UTM zone is built for NAG83, not for NatRef.
Mm-hmm. Well, excellent.
What's the timeline?
I'm sorry, Judy?
What's the timeline for datum updates once we get past these being introduced? Like, how are they going to be updated in the future?
So we're looking at when we first release the terrestrial reference frames, it will be at EPIC 2020.00. So NatRef 2022, even though it's coming out in 2024, let's say, it's still going to be called NatRef 2022 EPIC 2020.00. And then we're going to have regular, what we're calling reference EPIC coordinates every 5 years. So there'll be a new set of reference EPIC coordinates for all of the points and system for that matter in 2025 and again in 2030. It'll probably won't be until 2020, probably when 2027 comes out. Or I'm sorry, probably about the time, around maybe 2027 is when we'll release the 2025 reference EPIC. And then that reference EPIC will be valid from 2025. I'm sorry, from 2027 through probably 2032, at which point we will release the 2030 reference EPIC. The reason is because we have to take all of the data that we have and all the new data that's come in and recompute interframe velocity models and all of this in order to move that data and create this new reference EPIC. So it's not something we can do on January 1st of 2025. We have to. It's actually going to be probably a year to a 2-year project in order to redo that.
Great.
But thank you.
Yeah, so one last question and then we'll wrap things up. And I think this is a really good question. Are there any good published examples of a metadata checklist that would be asked for when data is submitted by others to document a survey?
I'm not sure. I'm not sure that there is one.
Yeah.
I did work. I'm trying to think who it was. Someone in our region, and if I think about it long enough, or actually probably when I'm not thinking about it, I'll think of it. But I had worked with somebody who was doing just that, trying to come up with a sort of a metadata standard for their agency. But I mean, I guess just fundamentally, obviously, you've got the frame, you've got the frame, the datum, the epic. You have and the epic is essentially the date of the survey, not the epic it's tied to, the actual date of determination. And then you have, you have things like methodology, and I think a lot of that is going to go into was it done with GPS? Well, that means many different things, right? It could be a resource grade GPS. It could be a mapping grade GPS. It could be, it could be something, a survey grade GPS. But even with a survey grade GPS, was it done using Opus? Was it done by doing a static survey tied to Harn stations? Was it? So you can see that there's, in every one of those is going to give you a potentially slightly different answer, even within the same, even within that same reference frame. Yeah, I think it's a good thing for discussion. I don't know that anybody has created one, or well, I know that it's been being worked on. I don't know of anybody who's actually created one, but I would think it's something would be good to develop profession wide, not just a single shop, but some kind of a GIS standard that. Because if that's great, it works great in my office, but as soon as I give you my data, that doesn't necessarily help you unless you understand and utilize the same metadata and metadata tags that I do.
Right. No, it's an ongoing challenge for sure. I think that's all we have time for today. I'd like to remind folks that we have a great Lunch and Learn scheduled for October. Please join us for that. But also don't forget our annual meeting in November will be a virtual annual meeting right here online. So we hope you can join us for that. And I'd like to thank Judy for her help, and definitely like to thank you, Dan, for sharing all this with us. We will post this on our YouTube channel, and we look forward to seeing everybody next month. Thanks again, Dan.
Thanks, Patrick. Always a pleasure. And for those out in the audience, questions, or pop me an email or give me a call. I'm happy to help out.
Yeah, there's Dan's email right there, dan.martin@noaa.gov. Thanks so much, everybody. Be safe, be well. We'll talk to you soon.
All right, thanks.
Thank you.